Here's what we'll talk about. We'll give a definition of what a priority queue is. Okay, you're already familiar with a queue. So priority queue is not a queue. Queue is the first in, first out data structure, right? So the guy who comes in first gets served first. For example, this guy came in earlier than that guy, so he will be served before this guy, right? So that's a queue. Everybody knows it. We have what is a queue as a data structure? Enqueue and dequeue, okay, or dequeue.
We kind of got an introduction to trees and then talked about binary search trees and different ways to traverse them.
Mm-hmm. Yes, the removal happens. Which element gets removed is what distinguishes this data structure from other, say, similar data structures like stacks. In a stack, which is also called a LIFO data structure, which means last in, first out, the item that gets removed from the stack at a given point is the item that last was added to the stack. In a queue, the item that gets removed at any given time is the item that had been there longest. Okay, so that's the queue. Everybody knows about queues. A priority queue is something that's different. In a priority queue, again, we think of items being added to a collection. The item that gets, the items are assigned what's called a priority. So the item with the highest priority gets removed first from the queue. Okay, you think of it, for example, as the patients in a reception room, in the hospital emergency room. Patients come in, somebody has a minor cut on a finger, somebody's having headaches, somebody's having stomach aches, somebody's having a heart attack, and so on and so forth. Well, a guy who's having a heart attack comes in, gets the priority service because it's medically a more dangerous situation than the guy with a minor cut on his finger, whatever. So the patients there get served by priority. That's the difference between a normal queue and a priority queue. So again, you still have the same collection, but the way the items get removed from the collection, or in this case, get served, is different for the two data structures. Okay, now, the main operations that a priority queue will support will again be insert an element into the queue, insert operation, and remove an element from the queue, sometimes called extract an element from the queue, remove, delete, and so on and so forth. We'll talk about Java has priority queue. We'll not use it. We'll implement our own version of a priority queue, but we'll look at how to use Java's version as well. Okay, so here's again an example of a priority queue. It can be a collection of numbers. So numbers, which number do you remove from the, so you have a bag of numbers thrown in. Which number do you remove first? You somehow added those numbers to the priority queue. Which one do you remove first? Well, you can have, depends on the priority. Which number gets the highest priority? Well, I can have some application where the number with the highest priority is the number that has the smallest value. Okay, then you remove always the minimum element from the queue. Okay, so delete min would be the operation to remove the smallest element from the queue. If the largest element has the priority, then you delete max would be the element to remove from the queue. Okay. So we'll find it very convenient to speak of two types of priority queues, although you can have one type as Java has it, and you can write some code to convert. It's easy to do, to convert a max priority queue into a min priority queue. But we will find it useful to have just two types. It doesn't take that much effort to write it once we grok how to write a priority queue, to have both versions. And depending on the application, we'll use the one that we find more useful or handy or appropriate. Okay, so we'll have a min priority queue and we'll have a max priority queue. This will be our API of the priority queue. So it's an abstract data type, it's an ADT. Here's the API for it. And now I'm kind of willy-nilly using these terms. You know what an API is. It's an application programming interface, meaning it's a list of those methods that allow you to communicate with the data structure itself. Abstract data type simply defines what this data type is, and it defines the methods that you can use on this collection. So you have something called max PQ that we'll call a bunch of elements here that will be a collection of elements. So some type, generic type E. And again, we're not spending that much time on this because we know about generics already. So generic data type can be integers, can be doubles, whatever, and they must be comparable objects. We'll see how and why. Okay, so you'll have these operations there: insert, delete, is empty, and so on and so forth, max and size. Okay, now these operations, we could have chosen other names for these operations. Other common names for the operations, for example, delete max operation is something called pull or remove. Okay, and to insert an item into the queue, you do offer, should be element E here, I'll change that. Offer an element to the queue, it inserts the element into the queue or add an element to the queue. If you go to Java documentation, in the handout that you have posted on Canvas, there's a link to the Java documentation and the list of the names of alternative methods that you'll see there. Okay, so if you use somebody else's priority queue, you should check what those methods do exactly, because there may be subtle differences in the way they're implemented and what they exactly do. But we'll keep things neat ourselves. We'll define our methods the way you see them on the screen, and that's what we'll implement today, or you will do at home. So now let's do a little bit of a demo. Let me switch here just to make sure that everybody's on the same page, and let's see what we have after the demo. Okay, this is kind of a, okay, so let's do this demo real quick. It'll take 2 seconds. Okay, so here's the demo of a priority queue. So you have a few items here. Those items are just kind of thrown into a bag. There's no particular order to these items. You have 68, 21, 77, 88, whatever. Okay, now suppose we have a min priority queue. Again, please help me out. What does min priority queue mean? So we have max priority queue and min priority queue. Anybody help me out? Is there anyone there? We have a few people only with, if you have a webcam, please turn it on. I know it's kind of maybe annoying a little bit for you that I say this, but I'm sorry, but yeah, let's turn the webcams on if you can. Yeah, so you guys see my screen, right? So these items are kind of thrown into the bag, no particular order. What is a min priority queue?
You look for the priority with the smallest value and pull that one first.
Yes. So the guy with the highest priority is the smallest element in the queue. So, okay, so we use poll. Poll is the one that if you use Java's priority queue, you'd call poll. In our case, in our version, we'll call this delete min or delete max to make it clear. So you poll this guy and run the first poll. The guy with the smallest is 21 in this case. So that guy comes out and is put is removed from this collection. Then the next one is 68. That guy gets removed. And I notice that this is kind of a silly demo, so I'm just moving some little balls around. But anyway, they will be arranged in an array. See this arrangement of an array? And now they're in sorted order, right? So based on this data structure, later we'll develop a sorting algorithm that we'll call heap sort. It's a nice sorting algorithm. Okay, we'll talk about that later. Okay, so where is a priority queue used? Now you have a handout also that's posted on Canvas. It gives a lot more examples, but here are the examples that we'll actually get to cover in this class. Dijkstra's algorithm. You'll implement the shortest paths algorithm, finding a shortest path between 2 nodes in a graph. You will implement this. You may have heard about this algorithm, but maybe never implemented it, or may have seen it in a math class. If you're taking some 2168 kind of class, you don't get to implement it there. You'll get to run the pseudocode of it, but not implement. Here, you'll implement Dijkstra's algorithm. This is the algorithm that lives in your GPS system. Okay, when you're getting from one place to another, that's run in the background. Slight modification of it. Heap sort we'll also discuss. It's a way of sorting the elements. There are many ways to sort elements. Why are some ways preferable to others? Who knows? Well, we'll discuss heap sort and then compare the different ways of sorting elements. Prim's algorithm, constructing a minimum spanning tree of a graph. We'll have to define what that is. It has to do with constructing a minimum spanning tree of a graph. Huffman coding, we'll talk about that. Maybe, I don't know, we'll get to talk about Prim's algorithm. Well, if we have time, we'll talk either about Prim's algorithm or Kruskal's algorithm. We'll see how things go. Okay, so we'll discuss some of these later. So this is just to give you a preview of the importance of this data structure. You'll have more examples in the handout that's posted in Canvas. Now, let me ask you, how would you implement? Now, let me switch back actually. So we have to do a little bit of, now I'm going to need your help. Okay, I've talked quite a bit. So let me share my other screen. Can you guys see the screen moving here?
Yeah, we see your slideshow.
Okay, okay. So let's implement. So what do we mean by implementing? So it's clear what we've just demoed, right? So all we have to do is we need a collection of items, a bag of items. Just throw items somehow, store them in the computer memory. You can store them in a bunch of different ways. You can use an array to store the items. Why not? You've always done this so far. You've either stored items using a linked list or an array. So what's wrong with that? You store all these items in the array, and when you need the maximum, you remove the maximum from the array. Seems like, so what is a priority? So remind me, what's a priority queue? I know I'm splitting hairs here and like repeating for the 17th time, but let's do it anyway. So just to be clear that everyone is on the same page when we talk about implementing a priority queue. What do we mean by this? So help me out in words.
Well, are you asking what a priority queue does or how we would implement it?
Well, I'll be asking both, but first, I guess the more general question, what does it do, just to review?
So you're pulling out either The highest priority or lowest priority object either by comparing them.
Yeah, so you're throwing something into a bag, we're storing something. So what's a good way? That's exactly right. So that's what I was asking, I guess. So how do we store the items? How can we, any ideas on how would we store it in an item? What do we do? How about an array, right? So you receive an item, you're processing something, you receive an item like 3, you store it in an array, in an array. So you allocate an array of sufficient size, you get an item, you store it there. Let this be an unsorted sequence. Okay, you get the next item, you store it there. Get the next item, store it in the next position. Get the next item. It's an unsorted array. Store it there, and so on. Or you can use a linked list. Also an unsorted sequence. It represents an unsorted sequence of elements. The linked list does. In this case, it's a doubly linked list, which we mentioned that we don't really care about those doubly linked list ones. But Java's implementation of a linked list is a doubly linked list. It's convenient in some circumstances. And often, most circumstances, I guess, to use a doubly linked list. It just simply means that each node has a reference to the node that comes after and the node that comes before. It's easy, it makes it easy simply to traverse that list in both directions. Okay, that's one of the few advantages of it. But anyway, here's a linked list, same elements, just stored differently. Now the question is, and we're implementing a priority queue. So what we need to do is simply insert an element. We already know how to insert it. Just put it at the end, in the array. And how about the remove element? So what do we do what do we need to do if we have the element stored in an array to remove an element of the highest priority? Somebody help me out.
You have to iterate through the entire list to make sure and compare everything to make sure you have the highest value element or the lowest.
Yeah, that's exactly right. So let's suppose that the highest priority is the largest element. So we're looking for the largest element all the time. So inserting an element doesn't take that long. It takes O1 time, right? Now at this point, it should be clear to everyone what I mean by O1 time, big O of 1 time. What's that shorthand mean to us? Big O of 1 time? Somebody help me out, please.
Constant time?
Constant time. That's the constant time. So it takes constant time to insert an element. You put it at the back of the array. You have space in the array, just put it in there. Every time you see big O of 1 in this course, in applications as a practitioner of programming and software development, constant time, big O of 1. Removing an element of the highest priority, how long does that take in terms of big O? So these are all good questions that we're discussing right now, all fair game for the quizzes, upcoming quizzes. Maybe not the next one, but the one after, which we'll talk about when the next quizzes are. We'll set the dates this week for all quizzes. So what's removing the element? How long does that take?
Big O of n.
Yeah, big O of n. Why is that? That's exactly right. Why is that?
Because you're comparing all the elements in the array.
Yes, yeah, that's exactly right. So we talked about this linear search, remember? So running this command, okay, offer element, if you're using Java's version, or our version will have insert e, just to distinguish it from Java's version. I mean, these are all informative method names. Inserting an element into the array, just put it at the end. Takes big O 1 time. Removing an element from the array takes or for that matter, the linked list, which is unordered, also takes big O of n. Well, takes big O of n time because you have to look through the entire array where exactly the large element is, because the elements can come in random order. So this is clear, right? This is one implementation. We have a perfectly fine implementation of a priority queue. We've stored the elements. We're able to run these two commands, these two operations on the priority queue. Insert an element, yes, we can. Remove an element with the highest priority, yes, we can. So what's wrong? Why even consider other implementations? Let's just all go home. This is it, we have it. Okay, but now we still have a little bit of time left. So we'll look at other implementations. How about a sorted array? What's the difference? So in the first case, I had an unsorted array implementation of a priority queue. How about the sorted array? How long does it take to insert an element? First of all, how long does it take to remove the element of the highest priority? In the previous case, remember it was big O of n. Now, if I'm sorting, if I always have the elements in ascending order, for example, and my delete max operation is remove the element, the largest element from the array, how long does that take?
Constant time?
Yeah, it takes constant time. Why is that?
Because it'll always be at the end.
Yeah, that's exactly right. So you know where the large element is. You just remove it from there. It takes constant time. How about inserting an element?
O of n?
Sorry?
Is it O of n because you have to sort it too?
Yes. So what are we doing? So let's be a little bit more fine-grained about what's involved in the insertion of an element. So what do we have to do to insert an element if you were writing code for this? Removing an element took big O of 1 time in this sorted array. But again, so we're at this, and one of you gave a good answer here, but we want to be a little bit more detailed. What's involved in inserting an element? All right, so let me show you the next slide. So here how you would insert an element into the array. First, you need to find a position where to insert an element in the array, right? Okay, can you use binary search to find the position where E goes? Right? Do people remember binary search? So suppose I want to insert an element like 8 into this array. 8 would go right in there, right in here, where 9 is. Okay, just to find the position for 8, I can use binary search, right? Where does 8 go? Are all of us on the same page why that's the case? But then, once I found the position for 8, I have to shift over the elements, like 9, 10, and 16 would go there so that I can insert 8 in there. Now that takes, how long does that take? Just shifting elements over.
Just big O of n.
Yeah, that takes big O of n time, because in the worst case, what if I'm inserting like 1 here? Then I have to shift all these elements over by one position, n of these elements. So in the worst case, this is big O of n time to shift all the elements. So I have something that takes big O of log n time just to figure out where to insert it. And then I have big O of n time to shift all the elements. And finally, it's constant time just to put 8 in there. Okay, so the total time of this is the largest of these guys, which is big O of n. Big O of n. Removing the element is easy, right? As you've just said, just the max priority that you always know in the array where the largest element is, it's at the end, so you just remove it. So now let's see what we have. Well, if you used like a sorted list, something like that, then your setup would be exactly the same, except that on the sorted list, you wouldn't be able to use binary search, right? Why is that? Can somebody help me out? It's still big O of n to insert an element. It ends up being big O of n. But unlike the array, where we found the position of the element in big O of log n time, this time we're not able to find the position where to insert the element 8 into this array. In big O of n time. We're not able to do it. Why is that?
You can't access elements of the linked list by index.
Yeah, exactly right. So there's no notion of an index. You can't just, that's the thing about linked lists. It's easy to rewire the links. And when it comes to accessing the element in the middle, you just have to traverse it. You have no other choice. If you have both pointers to the first and the last, and ways of traversing in both ways, like links in both directions from each node, then you can traverse from either direction. But you can't just, in constant time, access a middle element. But anyway, it still ends up being big O of n, this insert operation. And delete max operation ends up being big O of 1. Okay, so here's a summary of what we discussed. You can implement this priority queue. What's a priority queue? It's an abstract data type. What's an array? Sorted array, linked list. Those are data structures. So we have an abstract. So now in a moment, we'll talk about a heap, which will be a data structure like an array. So please note that people often confuse heaps, priority queues, same thing. No, they're not the same thing. Priority queue is an abstract data type. It's not a data structure. It's an ADT, it's an abstract data type. You want to use priority queues to solve problems, like for example in graphs, fast. Okay, okay? And to make that data structure, to make that, that data type, that abstract data type efficient, you implement it using an efficient data structure. What's an efficient data structure? We don't yet know. So far, we've considered arrays, sorted arrays, and linked lists as possible data structures to implement the abstract data type, which is the priority queue. So to implement the priority queue, the abstract data type, we use concrete data structures like arrays. And if we do use, for example, unsorted arrays, this is how long those operations on the abstract data types will be. So this is the measure of efficiency. It's a measure of efficiency. See, of these data structures, well, can we be informal as backers of the abstract data type priority queue? So we're using these data structures to implement the priority queue. As this is kind of very informal as backers. So you back with a data structure, an abstract data type as backers. This is not standard terminology of the priority queue. So, but there is another data structure. The point of today is there is another data structure called a heap that we can use. in particular, it's going to be a binary heap. Okay, there are the kinds of heaps that will allow you to do both of these operations in big O of log n time. Okay, so it will be more efficient. Notice that it takes slightly longer than insertion, for example, compared with the unsorted arrays, but it's much faster for large n to delete, to remove an element from the priority queue. So the trade-offs, you see the trade-offs? This is a recurrent theme in all of data structures. Yeah, they have three options here to implement your data structure called a priority queue. You can use a sorted, unsorted array list, you can use a sorted array or list, or you can use a binary heap. Depending on which data structure you use to back your priority queue implementation, you will get different efficiencies for these different methods, for these different operations. Which one is better? Well, don't know, because it depends on the application. The quiz is coming in a second. Is this clear so far? Well, wait, let's do breakout rooms. Okay, so here's a mini quiz. Do you guys see this? Right? So you have an array. So if you use an array, so insert an element and remove an element. Okay, these operations for an array in an array, insertion takes big O of 1 time, right? Removal takes big O of n time. X big O of n time. Here, insertion takes big O of n time, and removal takes big O of 1 time, which is constant. So the question is, here's a particular application. You're solving some problem. And you know that your problem is such that the number of calls, the number of elements that you have to insert into your data structure is roughly n. Okay, let's say it's exactly n, just to be concrete. It's exactly n. But you're deleting elements with a lesser frequency. That is, you only need to remove elements, only square root of those elements from the queue. This is from a real example could be. Okay, so which one is better? It's a typical quiz question, so why not practice it right now using breakout rooms? Can people figure this out? And just make sure you're just not listening, but also doing something during the lecture, please. So breakout rooms, let's spend no more than 5 minutes. Please start thinking, let's actively get engaged. Okay, are people back or? All right, so some people didn't join the discussion room. I'm assuming that you're just simply not here, you're logged on, and we're not aware that you had to join the discussion room because you're not around, you're logged on. All right, so what's the answer, please?
Wouldn't it be array?
Okay, so why is that?
Well, with an array, you have constant time for insertions and end time for removals. And since you have less removal calls, you spend less time doing ON calls.
Yeah, that's the idea. N time, you need to do N insertions. Here's the time taken by the insertion. And here's that many removals you're doing. Here's the time taken by that. So that's exactly what you said. That's exactly the answer. Did people see this? So you're doing this n times and you're doing this square root of n times. So roughly, this is big O of that much, right? If you chose the sorted array, because you're doing more inserts, you're roughly doing big O of n squared time. So roughly, again, these equalities are kind of loose. Okay, so but if you're a practitioner, you write equals big O, which is mathematically incorrect, but as a practitioner, you don't really care. So this is roughly the big O's. So big O of n squared would be taken by this if you used a sorted array, right? So you're better off using an array. Do people agree? Right, so I'll post these slides so that you can review before the quiz. Okay, so now what do we have? Now we need to know what a heap is. That is a nice, very ingenious data structure. Quite simple, very simple actually. Once you see what it is. Now this data structure, this binary heap, will allow us to efficiently support both of these operations: insert and remove from the priority queue. Now the items in this heap will be stored in an array. So notice what's happening here. We'll be storing this in a plain old array of, let's say, integers we have. Usually comparable objects, but let's stick with integers just for simplicity. It's easy for us as human beings to visualize these operations, like the structure of it, in a tree. Okay, a tree is just simply an aid for us to visualize a heap. Inside the computer, the heap is represented as just a plain old array. And here's what's happening. Let's say we want to store these 10 elements inside a heap. So we allocate an array of 10 elements. Notice that this is not a sorted array. This is not a sorted array, but the way the elements are stored inside array satisfy what's called a heap property. Now, what's a heap property? A heap property says that the element at any given node is larger than the elements of its children. Okay, so that has to be met if it's a max heap. Okay, that has to be met at every node. This, for example, here, what you see, is a max heap. The 16 here is larger than the two of its children, which are 14 and 10. Now, because 14 itself has to be larger than its children, okay, everything in this subtree has to be smaller than 16. Does that make sense? So what makes this heap, the storing a heap in an array, special is where these elements actually go. If you store a node in a given position, then its children are stored in positions twice that position and twice that position plus 1. For example, 16 is at position 1. Then its children, which are 14 and 10, are stored 14 and 10, which are children, are stored at positions 2 times 1, which is 2. That's where 14 goes. That's the left child. And 2 times 1 plus 1, which is 10, which is position 3. So notice what's happening. If we imagine these guys in an array arranged in a tree, and this will be a complete binary tree. We'll give a definition in a second what a complete binary tree is. First, let's get a feel of how these are represented. A complete binary tree is a binary tree, each level of which is completely filled out, except possibly the last level of the tree, where you start filling in the items, if you have them, from left to right. That's what a complete binary tree is. So you store 16 at the node, at the root node, which is node 1. Then its children go into positions 2 and 3. Now let's take any other node. Let's say position 3. The 10 is at 3, position 3. Where would 10's children go? 10's children go to 3 times 2 position. Notice in a tree where that happens to be, it's easy to see for a human being. It's at position 6, 2 times, or to 3 times 2 plus 1, which is position 7, which is right here. So what you do is you take up this tree and number these elements level by level. The root goes at position 1. The next level is completely filled out. So 2 and 3 go to the next level. How many elements are going to be at the level after that in the tree? Well, twice as many as you had before. So if at this level you had 2 elements, the next level you'll have 4 in a complete tree. Or if you have fewer, like when you move from this level to this level, the ones that you have are being filled in from left to right. That's what makes it, that's the definition of what a complete binary tree is. Does that make sense? So we'll give a 1-sentence definition in the next slides. For now, let's just get a feel of what that is. Make sense or it doesn't make sense? So you see how we're numbering this: 1, then 2, 3, then 4, 5, 6, 7. We're filling out each level from left to right. 8, 9, 10, filling out each level from left to right. 3's children will be stored at position 6 and 7. So let's take a look at 3. At position 3, you have 10. This is our 10 at position 3. 10's children are stored at position 6, which is 3, right here. 10's, nope, that wasn't it. 10's children are stored at positions 6, which is this, right here, and 7, which is here. Okay, so you'll see where there. So at 7 you have 3, and at 6 you have 9. Okay, do people see what's happening here? So it's an array inside the computer. These numbers, this heap, which will represent a priority queue, is stored in an array. But it's easy to picture this as a complete binary tree, a complete binary tree. So here's what This is what the heap ordered property means. This is what we need to know. So, okay, so is this clear? What heap ordering means? Okay, so which one of these guys is a heap? Should we do breakout rooms? All right, let's do breakout rooms with one, like just for 1 minute this time, because this is quicker, I think. Okay, so did we get any results?
My group said that neither is a heap because it violates the fact that the children should be only strict. The children that are on the left side should only be strictly.
Okay, so so that's one. So what's the heap definition again? Here's the definition. The key in each node is larger than the keys in that node's 2 children, if it has any. For example, the leaves don't have any children, so the leaves are fine. Okay, any other discoveries from other groups? Are we running out of time? No. Okay, we have
the second level of the first tree have to be fully populated for it to be a heap. Or sorry, the level.
Okay. These are not complete trees. Okay, the next remark will. So we can impose this heap ordering restriction on trees that are not complete. But in order to implement the priority queues, we'll use complete trees for that. Yeah, I should have mentioned this before. I gave you this quiz. Yes. So good point. That's an excellent point. But is that heap property met for these two? It turns out that for this one, it is met, because every time you see a node, so here it is. Every time you see a node, its children are in fact strictly smaller. So for 42, 29, and 18 are strictly smaller. For 18, let's say, its children are strictly smaller. The way we've defined them here is we're allowing keys to be equal sometimes. So this 18, there's only one child of 18. It has to be either strictly smaller or equal to it. In this case, it's equal to it. For each node, it is true that its children are either strictly smaller or equal to it. Okay. In fact, in this example, except for the node that says 18, every child is strictly smaller than its parent. How about this one, the second one? The second one, the heap property is violated in a bunch of places. So here it's violated. So here it's violated, 25 is bigger, and so on. So you see, like here it's violated, and so on and so forth. So the red edges represent the places where the heap property is violated.
I have a question.
Yes, please.
So for us to implement the priority queue, it needs to be a complete binary tree. For it to be a heap, it just has to obey the parent must be bigger than the child.
Yes. So the heap order. So we have a notion of a heap ordering property, right? That property, which is defined here, can be imposed on trees that are not complete. Do you see it? Just as in these examples. So it can be imposed on non-complete trees. But to implement the priority queues, we'll use complete. We'll see why it's useful to have complete trees to represent priority queues. We'll always use complete binary trees to represent priority queues in the examples that are to come, and we'll see why. And of course, in particular, in complete binary trees, you can impose that heap property, right? So
yeah,
right,
yeah, makes sense now. Thank you.
Yeah. So yeah, good point. So good questions, right? So this for example, neither of these trees is a complete tree. Those are binary trees, but not complete trees. In fact, somewhere below we have a review of trees, a couple of slides. Again, I'll post these slides. Okay, so you know what a tree is. I don't want to spend too much time on stuff that you know, but I just want to mention that there are different ways of defining trees. We prefer recursive definitions because your code will translate to recursive definition. And to prove stuff about the veracity of certain claims based on trees, you can use induction, so-called mathematical induction, which is a proof technique from math, which we're not discussing here. But you can use induction to make sure that certain properties that you claim are true about trees are really true. So this recursive definition is useful. So here's our recursive definition of a binary tree. Okay, something that's an empty tree is a binary tree. So it's an empty set is a binary tree. Just one node. And so you have a notion of a node in this definition of a binary tree. This is a node. A node is a tree. It usually stores some data that refers to two other structures that are themselves binary trees, right? That's a recursive definition. The entity that you're trying to define is part of the definition. That's what it means for the definition to be recursive. So I'm defining a binary tree here, and in this definition, I'm using a reference to other binary trees, which I haven't yet defined. That's what makes it sound a little bit odd, but it's not if you have a base case. Okay, so here's the left subtree, the right subtree, and we talked about what parent, children, siblings, height of a tree, all these things are. So height of a tree would like to give a recursive definition. Maybe we won't get to that today. So this is just a reminder, okay? And of course, this is a general tree. This is not a binary tree. But in general, a tree is a special kind of a graph. Okay? A graph is just a bunch of nodes, some pairs of which are connected with these things called edges. So this is a graph here, what you see on this slide here. And if you count the number of edges in a tree, if that graph is a tree, first of all, it's going to be connected. And you'll have exactly one fewer edge than the number of nodes. That's if that happens, you have a tree. That's an alternative definition of a tree. These are other alternative definitions. And it's a good exercise in math, or in logic, rather. It's not math, rather logic, to prove that these definitions are the same. But in this class, we're not spending time with this. Okay, but it's an excellent exercise to ensure that these definitions are equivalent in the sense that if you define the tree this way, these two other things must follow from it. And conversely, if you have defined the tree in any other way, the first definition, like this one, for example, would follow from it. But let's leave that alone. Okay, so this is an example of a binary tree, complete binary tree that you can find in nature. Okay, so you can find how many nodes. So the idea of a complete binary tree is this. Again, you have a notion of a level of a tree. So empty or no node that links to, so something like this that has null in Java and null here, that's also going to be a binary tree because these nulls are empty trees, will represent an empty tree in, so a null itself, that's a binary tree. This is a binary tree, okay? This, a node would make it a binary tree, would be a binary tree, and so on and so forth. So this one is a binary tree. Here's the root. Then at this level, you have twice as many nodes as you had. So number of nodes, 1. So number of nodes in the second level is going to be 2 times 1, which is 2, and so on. So a number of nodes in the next one is going to be 2 times 2, which is 4. The number of nodes here is going to be, on the next level, is going to be 2 times 4, and so on and so forth. Except possibly, okay, so on the next level, you'd have 4 if I put these, right? So do you see, do people see this? Except possibly for the last layer, or last level, where if I have some extra nodes, I begin filling those in from left to right. So now, when you count the nodes, now I'm going to count these nodes as entries in an array. So I'm going to count in such a way that the count associated with each node will be the same as the index in the array in which I store this tree. This tree will be stored as an array. Let's do some demo. Let's get straight away to the demo. Okay, but let me tell you about the array. So here's a tree. Is it a complete binary tree?
Yes.
Yeah, it's a complete binary tree. I mean, some images are drawn longer just to put them on the here, but this is the root. It gets at position 1. This is where you store t. Now twice, the guys at the next level are at positions 2 and 3. 2 and 3, so that's where they are. The guys at positions, okay, well, what is this p here? P and n. Okay, they must be strictly smaller than s, right? So in this case, the ordering is alphabetical. So P and N come before S. So those will be stored at positions 4 and 5. So twice 2, that's 4, and twice 2 plus 1, 4 and 5, and so on. So that's true for every node. Okay? The largest element is always stored at position 1. Notice that we're ignoring position 0. There's nothing stored at position 0. You could start storing at 0, but then you'd have to play with the indices a little bit. I think it's easier to start at position 0. The point is that the parent of any node is at position k over 2. So where's the parent of O, for example? R is the parent of it. So that's stored at position 3, so half 6. What's the parent of A? The parent of A is R, and that A is stored at position 7. So 7 divided by 2, if it's integer division, is going to be 3. So that's where it is. Okay, the advantage of this array representation is that you can easily find where any node's parents or children are. And that will, we haven't gotten to the heap yet. We want to use this convenient way of storing the elements of a tree, of a complete tree, make it a heap to represent priority queues later. That, I guess that's going to come later. Okay, now, how do we remove and add elements to the priority queue, to this heap, without violating the heap property? I'm going to switch over to my, so we can do the demo. Where's my switch over? Here's a tree. Is this a complete tree? Is my question number one. Yes, it is. You will say, yes, it is. But is it, does it meet the heap property? That is the heap property, heap ordering property, satisfied for this tree? Well, you look at S, its children are smaller. If you look at R, its children are smaller. O and A both come before R in the alphabet, and so on. So you check like every node, and at some point you'll discover that here, this heap property is violated. Okay, so this is not a heap. So we want to have an operation that restores the heap property. And by the way, take a look at the bottom of the screen here. It shows you the array representation of this heap. Right? Do people see this? The array representation of this heap. So S is stored at 1. S children, P and R, are stored at positions 2 and 2 plus 1, which is 3 here, P and R, and so on. So where are P's children? P's children, because P is stored at position 2, its children will be stored at positions 4 and 5, right? Twice 2 and twice 2 plus 1. That's easily seen in a tree. That's why we like to have a tree representation. Inside the array, P will be at position 2, and its children, N and T, will be here. N at position 4 and T at position 5. Now, when I looked at this tree, that is, examined the array entries, which you will in code, you'll see that T is in the wrong place. So it violates the heap property because T is larger than P. It comes after P in the alphabet. That's why it's larger. Maybe it's easier to see with the numbers, but we don't want people to confuse the numbers that represent the indices with the numbers stored there. I guess we could have had 2-digit numbers there. But you can see if you can compare the letters in the English alphabet, then it's obvious. So T is in the wrong place. What do we do next? So we simply exchange these two elements. Now, when we exchange these two elements, it so happens that T now violates the heap property. Do people see this? So T now is larger than S. So you have to do another exchange. And now, at this point, the heap property is restored. So when the heap property is violated, you'll have to do the number of some number of exchanges. I'll ask you in a second what's the maximum that number can be. Some number of exchanges so as to restore the heap property. Now, can I ask you what the maximum number of those exchanges is? What's the max number of exchanges you would have to perform if you were storing these elements in an array like this, which is a complete, which in turn is a representation of a complete binary tree?
Log n.
Yeah, why is that?
The easiest way for me to think about it is you're kind of doing the inverse of the squaring operation in terms of what you're eliminating every time, if that makes sense. So you're kind of
yeah. It should make sense, and not completely. You would have to a little bit be more precise with language, but yeah, it will make sense in a second. So how did you think of it again? So maybe I misunderstood you.
It's kind of if you take a root of 2 out of your input n every time, that's kind of the possibilities you're eliminating every time you shift it up in the tree.
Okay, so I'm going to sort of rephrase it, and you tell me if that's what you think. So the maximum number of operations you'd have to do is to exchange the element that's at the bottom in such a way that it ends up at the very top, right? That's the maximum number of operations you'd have to do. If the heap property was violated somewhere closer to the top, like here, you would just simply exchange these two. And then maybe you'll have to check for something else, but we'll see. Exchange these two. But if the heap property is violated here, then you might have to what's called swim this element all the way up. Sometimes this operation is called swim. Sometimes it's called bubble. We'll call it swim just to settle in something. It bubbles up. So imagine these guys, these nodes at the bottom, like sunk like below. This is the depth, like deeper down the tree. So it has to swim up to the root. And because the height of a complete binary tree is at most log n, it cannot be bigger because, and here's why it's useful to have a complete binary tree. In general, the height of a tree can be like n, right? As we saw last time. Do people remember? Like this path graph of n elements, that's also a tree. It fits the definition. But if I have a complete binary tree, then the height of this thing is at most log n. Well, the floor of it, but let's not worry about that. So this operation takes at most log n time. Okay, so here's how this operation is so nicely is implemented in Java, the swim operation. You will implement these things, okay, in Java. So I'll post these notes, and it relies on just swapping array elements. So this exchange, you will have a helper function exchange. You know how to swap elements in an array, you know. So we'll give this code. So exchange means swap to or swap. You can call it swap if you'd like. So I'll let you implement this on your own. I mean, at the end of the day, the answer is here, but people should go through this. We also have what's called a sync operation, but let me see. Let's do a demo. So here's, we want to insert suppose we now want to insert something into our heap, okay? So this is our array representation of the heap, and here's the way we picture it in our minds as a complete tree. Now, this is heap ordered right now, if you check it. Now a new element comes in. So you want to order S, add this S into the heap. The first thing you do, you append it at the end, at the very end, meaning you put S in here, at the end of the array. But now, here's what you do. You'll notice that it violates the heap property. So you have to swim this guy up to insert this element. So exchange it with S, okay? You see what's happening with the array and the tree itself. You do these exchanges, okay? And now the heap property is ordered. So I've rearranged this array on the bottom, and it's now heap ordered. This is a complete tree that meets the heap property. It satisfies the heap property. Now, suppose you want to remove an element. This is a new operation. So we'll have two operations, sync and swim. Now I want to remove the maximum element. Okay, so T is the maximum element. This is how you do the removal from the priority queue if it's the delete max. You take out the root from the tree, but now if you take out the root, you're now no longer gonna have the tree. You somehow have to make it a tree and also restore the heap property. How do you do this? Well, first of all, look at the last, so let me go back one slide. So this is what your tree looked like. To remove T, you first look at the very last element in the array, which is H. That's gonna be on the bottom of the heap at the very last level. Do people agree? That has to be at the last level. Now, the next thing is you exchange these two. These are only a few Java operations. You've exchanged these two. Now the heap property is violated, right? This violates the heap order. Now T you can get out. So T is now just decrease the size of the array, so T is out. So you're not worried about it. You've already returned T to the client of this code who wants to do delete max. But on the background, you have to keep that data structure intact, meaning that the heap property should be at all times maintained. That will be the invariant of our data structure. So to maintain the heap property, we must, well, restore the heap property. How do we do this? Well, whatever violates the heap property, notice how H is being sunk down to its proper position. It goes as far as it needs to in order to restore the heap property. Do people see this? Okay, now again, let's suppose we have another remove max element there. So I'm removing max. Let's go exchange with the root. Do people see this? Go on, violates the heap order. Do people see how this is done? So suppose now we want to add S. So now you help me predict what's going to happen here. First of all, I don't know why I'm showing you the whole attendance sheet. You shouldn't be seeing other people's attendance, I guess. I don't know, not that it's that big deal, but still. So what do we do now? So help me out. So I want to add S. So here's my heap. This is the heap. Now I want to add S to the heap. First thing I do is I put it at the end of the array at position 10, as you see there. Now it's there, but the problem is that it violates the heap property. So I need to swim this guy up to its rightful position in the heap to restore the heap property. So you swim it up by exchanging it with its parents up to the point where it needs to be exchanged. In this case, it goes all the way up to the root. So that's log n swaps. We count the efficiency of this data structure by the number of operations we need to perform. I think we should end here.